Great, welcome everyone. Today we'll be hearing from Dr. Dawn Anderson. Dawn is a professor at the University of Iowa in the Department of Orthopedics and Rehabilitation. And he is currently a Killam visiting scholar here at Calgary. Dawn completed his bachelor's, master's, and PhD at the University of Iowa in biomedical and mechanical engineering. His PhD was supervised by Dr. Thomas Brown, and he explored finite element analyses of impulsive loading on a rabbit knee, a model for load-induced osteoarthritis. In his first postdoc position, Dawn directed a biomechanics research laboratory at Allegheny Singer Research Institute in Pittsburgh, Pennsylvania, for 7 years. There he studied intra-articular fractures and upper extremity biomechanics. He next moved to Minneapolis, Minnesota to direct a new biomechanics laboratory at the Minneapolis Sports Medicine Center. There he conducted sports medicine research related to the shoulder and rotator cuff. In 2002, Dawn returned to Iowa City to join the Orthopedic Biomechanics Laboratory as a research engineer. He moved on to a research faculty position and is now a tenured professor. Dawn's primary research interests are understanding pathomechanical risk factors for post-traumatic osteoarthritis after joint injury to inform clinical studies of new treatments aimed at preventing this disabling outcome. He has also been exploring the potential utility of weight-bearing CT for evaluating articular joint preservation. Dawn's proudest accomplishment is leading a team that won the 2011 OREF Clinical Research Award, one of the most prestigious awards in orthopedic research. A few fun facts about Dawn. He is an identical twin and one of 5 boys born to a family within a 5-year period. He hiked and skied Mount Yanuska with Brent in June of 2018 and lived to tell the story. And he loves to homebrew beer and ferment wine. So with that, I'll turn it over to Dawn. And as a reminder, Dawn will first give his presentation, and then we will have a question and answer period to follow. And at that time, I'll remind everyone how to submit a question. So thanks in advance, Dawn.
Great, thank you for that introduction, Emily. I always feel like when somebody tells my work history, I almost feel like I have to clarify one thing, because I think for young people, it can be kind of an encouragement, but the job I left in Minneapolis was not of my own accord. It was actually, I was laid off, and I called my graduate school advisor, Tom Brown, who said, I just got a grant funded and I could really use somebody to do some work on it. And that led eventually to a tenured faculty position. So sometimes getting laid off is about the best thing that can happen to you. It shouldn't be something you're afraid of. But anyway, today I'm gonna share some of our work funded by the Department of Defense. This is titled here, A Computational Modeling Framework to Assess the Effects of Carbon Fiber Bracing on Ankle Joint Function and Contact Mechanics. We're still relatively early in this latest turn in our research, and I'll be really interested to hear questions and get feedback from folks. And really, I only have one name on this, but I'm presenting work done by an entire research team at the University of Iowa. And one of those people is on our Zoom with us, Jason Wilkin, who's the primary collaborator and a really wonderful partner to have back at Iowa after having done his PhD, went away for a while and came back to us. So I am a Killam visiting scholar, and I wanted to thank Walter for hosting me here. Interestingly, here's the timeline. The application was submitted in December of 2019, just before certain something or other happened in our world. We were notified of the award in February 2020, and we planned for me to come January to June of 2021. That didn't work out so well. So then we planned July to December of 2021. That didn't work out so well. So here we are, January to June 2022. Perfect for us here. And a wonderful time to come to Calgary. I've really enjoyed some snowshoeing with my wife, Jane, who's accompanied me here. This is that first weekend we had up, and this is snowshoeing around Johnson Lake, and what a wonderful day that was. So I always like to start with telling people where Iowa City is. Hopefully you can figure about where Calgary is there. Here's Iowa City in the middle of Iowa. It's not too far from Chicago. I can't remember if you can see my cursor at times. Chicago's over here, about a 3.5 hour drive. North to Minneapolis, about 4.5 or 5 hours. St. Louis is down here. So we're kind of in the middle of a area with a lot of larger areas, but none of them are closer than about 3.5 hours away. What is Iowa City? For those of you who don't know, actually, Walter Herzog did his PhD at the University of Iowa, left Iowa just shortly before I finished or started my PhD, excuse me. Iowa City was the original capital of the state of Iowa as people moved west across the US. And the old capital still exists. It's kind of the primary icon at the center of the University of Iowa campus. As things moved westward, later the state capital was moved to Des Moines in the center of Iowa. It's kind of got some interesting contrast, just like Calgary. Here's the Performing Arts Center, a really stunning building on the Iowa River in Iowa City. But if you drive about 10 miles from there, this is what you'll see in certain time of summer. Most of Iowa is about corn and soybeans and pork production. But the University of Iowa does have one historical artist we like to draw out, Grant Wood. For those of you who don't know, he was a American regionalist painter, this idealized style to represent the landscape of Iowa. American Gothic is a class that is often recognized and, dare I say, oft memed on the internet. But biomechanics wisdom from Iowa goes back quite a ways. And I like to introduce people to Arthur Steindler, the department chair when the orthopedics department at the University of Iowa was first founded. And this was actually a statement he made in his presidential address to the American Orthopedic Association. Biomechanics is a powerful and indispensable ally of the orthopedic clinician. I don't know if it was a heretical thing to say at the time, but I certainly think it was a step towards our department having a very specific slate of key differentiating strengths. Our biomechanics research is closely tied to clinical practice, involves complementary testing, image analysis, computational modeling, is truly interdisciplinary. And that openness to collaboration I mentioned too led to the Killam Visiting Scholar Award that I mentioned. We actually wrote this first, didn't know if it was going to be funded, so we wrote a second grant I did with Rami Korhonen at the University of Eastern Finland, and we had the double hit. They both got funded. So this is a way to try to catalyze some research between the University of Calgary, University of Iowa, and the University of Eastern Finland. But let me change topics a little bit now and get into the meat of this presentation. So post-traumatic osteoarthritis is clearly a disabling major economic burden. It's well known that they're predisposing joint injuries. We have chosen to study intra-articular fractures, largely of the tibial profound, and I'll tell you why shortly. But we've come to recognize two key pathomechanical risk factors: the original acute fracture severity and the chronic contact stress elevation associated with these being put back together imprecisely. We started in the ankle because ankle arthritis is generally rare, but after trauma, it's greater than 50%. And it occurs early, usually within 2 years following injury. So that's a pretty good clinical model to study, because if you want to change anything, you only have to wait a couple of years to see the results. The etiology is unclear, but mechanical factors are clearly implicated. And until recently, those were difficult to objectively quantify. The acute fracture severity is where I usually start, and I inherited this work from Tom Brown, who had the original idea. But fracture mechanics helps us in this case. Energy stored in a structure when loaded, and the failure initiates when the loading exceeds the capacity of the structure. And energy is liberated in the fracturing process. You can clearly see that in this video. And in brittle solids, which bone certainly is at the rates of loading fracture often occurs, the fracture energy is proportional to the fracture liberated surface area. And that's been known since back in the mid-1800s. So we use this methodology to develop acute fracture severity metrics that are objective and based on the physical principles of fracture mechanics. And interestingly, when you take this fracture severity is based on, I'll go back one slide, excuse me, based on a preoperative CT scan. So on the right-hand side, you kind of get a sense of that. So this is before the surgeon has started to considered treating this patient at all. A CT scan is acquired. And so that fracture severity metric from that preoperative CT scan correlates very nicely with PTOA risk. So on the y-axis here is our fracture severity metric. I've actually normalized it here. And then I've got a stack of 20 cases here, and each of these columns is a different case where I have the height of the column is the severity, objective fracture severity metric. The color is whether they developed arthritis 2 years later by KL grade. Green, they did not. Yellow, they're kind of in the middle, and red was severe osteoarthritis 2 years later. And what we were able to do is nicely show that PTOA risk scales with the acute fracture severity. And that's kind of amazing in its own right, because that means before the surgeon did anything, this was a risk profile here. And we developed methods here to be able to move quickly from a CT scan that's acquired preoperatively to computing fracture severity. And I have now done this on the order of 500 different joints in the body. The other is, I mentioned chronic contact stress elevation, and we developed a patient-specific finite element modeling workflow to look at this. And I'll just tell you, here are those same 20 cases, some of the most heavily studied ankles I've ever known. You may, if you look closely at these, you may see screws that are in these volumetric renderings. And that's because these were acquired after the surgeon had fixed, quote unquote, fixed the ankle. And of course, things are left in an imperfect state sometimes just because of the challenges of putting Humpty Dumpty back together again here. So we developed a methodology to take those post-op CT scans and generate finite element analysis first, and then later a more simplified contact stress computation called discrete element analysis. And this DEA allows us to come up with quick predictions of contact stress based on the post-op CT scan. And with that, again, the x-axis here, it's a little complicated, but this is a stress time overexposure metric, and how much of the articular surface saw elevation in this stress time overexposure. And on the y-axis is whether somebody developed arthritis or not based on the KL grade. And what you can see here again is that there's a clear link between PTOA risk and this overexposure metric. So how well the surgeon puts it together is another key factor that hadn't been measured before. So we've since developed weight-bearing CT methodologies. And of course, a CT is not a standard post-operative investigation and involves higher doses of radiation exposure, and a person is on their back, so it's not weight-bearing. Instead, now we acquire 6-month weight-bearing CT scans, which are lower dose and are already in a weight-bearing pose. And these then allow us to come up with contact stress predictions. So this is all a prelude to the work. When I had done some of this work, I actually presented some of it here several years ago. The question was always, so what? What's the surgeon going to do after the surgery is done? They can't really go back in and fix that imprecision. They already did the best they could. And we were kind of stuck at that point until Jason came back into the works and was talking to us about some bracing alternatives. And we wondered if, in this line of research, we could advance intra-articular fracture treatments and lessen the risk of P2A by addressing the risk factors after surgical treatment. And so on the right is a carbon fiber custom dynamic orthosis brace created for an individual. So when we think a little bit about ankle bracing solutions, these are devices to limit the position and motion of the ankle, provide support. They're used to address a wide range of lower extremity deficiencies. I'm sure you're all familiar or know somebody who might wear one of these. The ankle foot orthoses are kind of the most well understood, prescribed generally in this realm. However, none have directly addressed ankle intra-articular fracture recovery in our efforts to try to reduce P2A risk. Jason brought back this ideas or these concepts from his time in the military at the Center for the Intrepid, where custom dynamic orthoses were used to return people to a high level of function even after severe limb extremity trauma. And these are a subcategory of AFOs. if you look closely at this video, which I love, you kind of see the posterior strut of this brace flexing and loading. And that's part of the idea. And you can see on the anterior portion here, this cuff is kind of allowing some load transfer there as well. And it's relatively rigid foot plate, so you're not seeing a lot of foot motion either. So CDOs possess the ability to be custom tailored. And because they can be custom tailored to the geometry of the limb, you can get very nice load transfer here. So here's some of the design elements I mentioned after looking at that video, whether it be a posterior carbon fiber strut, a cushioned heel wedge, or this custom molded foot plate, or even the proximal cuff, all elements to try to control the ankle motion and support it. And this addresses functional deficits after limb trauma. Prior work that Jason had been involved with had very well established this. I'll just quickly run through this. It's actually a pretty impressive combination of papers put together here, looking at how the CDO design influences limb mechanics and improves outcomes in injured service members. So this is pretty much a well understood fact. But again, they may also reduce ankle contact stress. And we identified, as I said, this is a primary P2A risk factor, either through mechanical offloading, the use of the heel wedge, et cetera. And we hypothesized that plantar flexor muscle force reductions could induce reductions in the joint reaction force and contact stress that might be beneficial. So if we think a little bit about the muscles at the ankle, the gastrocnemius and soleus form the triceps surae or calf muscle, which controls foot plantar flexion. And in a healthy normal gait, this muscle force is exerted through the Achilles tendon, which stores energy during mid-stance, returns it in late stance, thus propelling the limb forward. Here's a simple free body diagram to bring up the possibility that if we can kind of introduce a CDO that reduces the moments about the joint, will also reduce the force in the, or excuse me, by reducing the moments, we'll reduce the force through the Achilles tendon, which will correspondingly reduce the ankle joint reaction force. So here is our overall study vision. Develop some kind of modeling system. At the beginning, it was as simple as thinking connecting OpenSim somehow with our DEA to use some kind of gait data. We wanted to collect some in vivo experimental data to incorporate different data sources, and then perform a cadaveric validation of our modeling methodology. So quantifying joint contact stress starts with a gait lab assessment. Out of that information, we take the gait kinetics, kinetics and kinematics, and also the CDO stiffness, and introduce those to an OpenSim model. And we've scaled a generic model that's been out in the literature. I'll tell a little bit about this in a few slides. But then turn that finally, if we estimate joint reaction forces from OpenSim, feed those into discrete element analysis, and based on bone geometry obtained from the weight-bearing CT, be able to generate estimates of the contact stress. And here's the basic pipeline of this workflow. I don't want to belabor the point, but we've developed a little CDO prescription console that allows us to potentially change CDO design features and see how it influences the contact stress. So here's the patient-specific modeling workflow. I'll just walk through this a little bit. I won't spend a lot of time on any individual portion of this, but it starts certainly with a data collection in the gait laboratory, either kinematic marker data collected, subject height and weight, and then ground reaction forces with the force plate. Jason, as part of our preparation, had done prior work to document that he could reliably assess gait kinematics and kinetics in his laboratory. This is the motion capture system in his laboratory at the University of Iowa. And here's the marker set that he uses. Close up looking at this. So the data processing is done in Visual 3D, where the data is low pass filtered, scaled to subject height and mass. And then the inverse kinematics least squares optimization algorithm is used to add physically realistic joint constraints to the subject model to restrict relative motion between segments and minimize the effects of errors from soft tissue movement. So then how does that interface with our modeling in OpenSim? Again, for those who aren't familiar with OpenSim, it's a musculoskeletal dynamics modeling pipeline. It's designed to study kinematic and kinetic motion of subjects, allows for gait analysis of all lower limb joints. You numerically solve for the dynamics of motion. And in our case, when we apply forces such as would be associated with the CDO, we can study how that might change the muscle forces and motions. Here's the OpenSim processing pathway, scaling again to match experimental markers from that generic gait in the OpenSim model we were using. Inverse kinematics, we match the generalized model coordinates with those experimental markers. Then we have to do a reduction of residual analysis. And then there's a static optimization used to generate the muscle or predict the muscle forces. And here's kind of a graphic showing you that pipeline. And then the question becomes, how do you introduce a brace in this system? So we've studied a couple of different ways to do this. We settled on adding what's called a coordinate limit force to the model that can effectively simulate a physical CDO by representing its rotational stiffness and neutral ankle angle. So this is the basic idea, is that at that joint at the ankle, there's a coordinate limit force. The stiffness varies with the coordinate angle, and we can choose where this falls based on what shank to vertical angle is introduced, and how stiff the brace is going to influence how the coordinate force moment angle is resisted. Just glancing at the gait cycle, of course, most of you are familiar with the stance and swing phase here. You see how the ankle angle and joint reaction force progress through the stance phase of gait, where we primarily focus here. We do not use muscle force or excitation patterns as part of the prediction, but we do use it to kind of corroborate our predictions. And that's, here's the data collection methodology here. And this is kind of our little touch point. The conditions from left to right are a no CDO on an ankle. And then there's 3 different CDOs that I haven't spelled out what they are, but from left to right, 3 different bracing strategies. And here's on the top panel are the muscle excitation patterns for the gastrocnemius and the soleus. And on the bottom are the OpenSim force predictions in those same muscles. And although we're not totally pleased with this, we do think there's a pretty good agreement with the gastrocnemius in particular. The soleus, there's some issues that we're still trying to understand a little bit better. But we're pretty happy with this corroboration. Then we also have load sole, insole pressure sensors we put in. This provides precise, accurate, and repeatable measurement that allows us to look at the heel, midfoot, and forefoot distribution of force transfer. And again, here's that forefoot loading shown in the presence of a brace or CDO and without the CDO. So one of the things you can see is that the CDO certainly does restrict the motion and force here at the ankle joint. Or excuse me, this is the forefoot loading, sorry. So now we take those outputs from the OpenSim model, muscle forces, joint reaction forces, corroborated by our other experimental measurements, and we can combine those with this joint model from the weight-bearing CT to predict the tibio-talar contact stress. So that completes the workflow. Here's the weight-bearing CT scanner, since been replaced by a different scanner design in our lab, but here's the curved beam scanner that allows you to do nice weight-bearing scans of these ankles. Discrete element analysis builds models off of those tibio-talar joint, the talus bone and the tibia bone. The cartilage is modeled as a bed of compressive springs between 2 rigid bodies, the talus and the tibia, driven together by external forces or motions. So here you can see where the tibia and talus bones segmented from CT scan, and then the articular cartilage, anywhere where we see an overlap in the articular cartilage, which is represented centrally here. Those springs or cartilage will have to carry that load, and that's how the contact stress predictions are made. And this just shows you basically what that can kind of look like. whether you choose to analyze it as a distribution or whether you parcel out portions of it to see if you can effectively reduce the contact stress in one portion or another. So just first, a preliminary case study, and then I'll show you a couple of other results as well. So this is data from an individual with a post-traumatic injury that required CDO use, collected in Dr. Wilkins' laboratory. And we use the modeling framework to compute muscle forces, ankle joint reaction forces, and contact stress exposures. And we looked at 4 CDO rotational stiffness levels here, ranging from 0 to 5 Newton meters degree, obviously 0 being our unbraced condition. What we showed in the modeling is that the plantar flexor muscle forces indeed were reduced as we increased the stiffness of these CDOs. And to the right shows you the ankle joint reaction force, which is also reduced with those stiffer braces. That correlates, perhaps not surprisingly, to reduced contact stress time exposure or overexposure here, whether you look at the maximum or the mean. We found a 22.3% reduction in the mean contact stress time exposure relative to the unbraced condition here. So we conclude from that that the contact stresses at the ankle may be meaningfully reduced with CDO intervention during gait. And we then went on to do a data collection in a series of healthy subjects where we varied the braces and made specific data collections here. We had 4 conditions in these 6 healthy subjects, no CDO and 3 different CDO braces, which I'll show you in a second. We gave instruction and 5 minutes of accommodation time for each device. And the accommodation time is important because these braces, an individual can kind of fight these braces. They take a little getting used to when you first use them. So here are the three brace designs we studied. A little variation in kind of the proximal cuff, and you can see some variation also in the foot plate itself. And the stiffness numbers are shown here, collected in the laboratory. So if we analyze the effects of these bracing, you can see how the brace on the right shows you how you get reduced motion when you're wearing the brace. So you're reducing the ankle motion some. And the ankle joint reaction force is also reduced. And that's what this shows here. Interestingly, these 3 different brace designs influenced not just the stiffness, but the design themselves influences the reaction forces that are calculated. So when we look at the soleus muscle forces, the CDO condition significantly reduced the peak soleus muscle force. And I show you that on the right here. And in terms of numbers, that's between a 30 and a 45% reduction in the soleus muscle force. In the joint reaction forces, kind of comparably, we saw a 16 to 30% reduction in the joint reaction forces. And then when those were turned into our contact stress time overexposure measures, here you see in a single ankle, those 4 different cases, the CDO significantly reduced the cumulative contact stress time overexposure between 16 and 23%. So carbon fiber bracing is an attractive intervention option for preventing PTOA following intra-articular fracture. They can significantly reduce the axial ankle joint reaction force, the soleus muscle force, and by extension, the contact stress time exposure. We have work still to do. The primary focus right now in our laboratory is to do some cadaveric validation of some of these force predictions come out of the OpenSim model. And I've just shown you a little graphic here to give you an idea of what we're trying to do there with tech scan pressure sensors and a brace introduced in our loading system. So I'd like to acknowledge the help of Dr. Ann Silverman with some of the early OpenSim work, the graduate students who helped in this laboratory or in this work, and the Human Performance and Clinical Outcomes Lab members. And of course, I need to acknowledge my funding sources. And I haven't even looked at the clock, but I thank you for your attention. And just in case you were wondering, that is me at the peak of Mount Uninska before most of the skiing actually happened. So thank you for your attention, and I'm happy to take any questions now.
Thank you, Don. Great. So at this time, I kindly ask the audience members to turn on their camera if they're comfortable to allow for a better discussion. To ask your question, you can use the raised hand function on Zoom, And if you're unable, you can type your question in the chat box and I will read it aloud. Art, please go ahead.
Yeah, I have a question about the, at the beginning, you said you were doing an inverse kinematics correction to get everything to sort of fit right. And I was just wondering whether that causes any, I don't know, artifacts or things in the calculation of the contact stresses, because it seems like when you're calculating contact stress, that partially depends on some, deformation that's going on in the joint. And so you're pressing two surfaces against each other. And so if there's a kinematic constraint that's sort of forcing things to basically be constrained along a certain surface or something, I guess my concern is that constraint would basically prevent the surfaces from pressing into each other, and then could lead to some sort of strange measurement of the stress or the force. So I'm just wondering whether that's a concern.
Yeah, Art, that's a good question. So I think it's probably an inadequacy of my presentation, but I think that was earlier in the talk when I was talking about how the marker data set and that motion was being used to generate the kinematic profiles. Since there's obviously some soft tissue deformation, some other things. So I think that Jason would have to tell you his timeline of how he came to use that methodology. But I think that's a standard methodology to try to accommodate the connection between the motion data from the marker set and the kinematics that you're going to apply to the joints. But it's certainly, yes, everything in this pipeline has some implications for the contact stress prediction, absolutely. So I think we need to follow best practices along the way, and we have a validation burden ahead of us too.
Mm-hmm.
Maybe just to follow on to Don's comment, I think you're on point in terms of the constraints that we're applying, but those constraints primarily are determining what we're feeding into OpenSim. Whereas when the DEA is performed, that's simply using the joint angle. So it's essentially the tibio-talar position, as well as the joint muscle forces. And so Don's model isn't constrained in the manner that you're getting constraints during visual 3D assessment or analysis.
Brent, are you going to leave your hand
Brent,
raised? Or?
Yeah. I guess further to the validation burden. So we do this kind of stuff too, where you do sort of the motion analysis, which I think has, there's quite a bit of noise and error involved when you try to estimate the forces at the level of the joint. And then, we apply them to finite element models. And it's really sensitive to, where you say the point of application of the forces to the, and so I'm just wondering, like, what do you assume for your for the discrete element analysis? Like where do you, where does the center of the load go? And like, when you do go to validate this thing, are you thinking of trying to do some dual fluoroscopy or something like that to sort of confirm if you're?
And we tend not to validate with technologies we don't have available. So the dual fluoro would be off the table for us. So we're starting with cadaveric validation, which we're pretty comfortable with. But so the DEA, I think we use standard ISB type approach to identifying a joint center there. Try to coordinate that with the kinematic model that's used in the gate collection. I know at first we had some headaches there to sort, but we got those sorted out pretty well, I think, to where we feel comfortable transferring between those two platforms. I do think that when a person's doing it with a load application, it's different than when you're doing it strictly a kinematically driven model. Kinematically driven, obviously, it's going to generate as much force as it has to generate the bone motions you're trying to do. But if you're shifting to what's essentially a load control, then I think you kind of have a little more leeway. I guess that would be my best answer for that.
Yeah. I have some questions about kind of like, the insurance, like right now, there's a grant that's paying for this. But, in the long term, like, our insurance company is going to pay for, weight-bearing CT, or are they gonna, want to pay for the, the personalized development of the bracing?
Yeah, so I think, I guess my answer to that, I have two answers to that. One, I guess right now they pay for radiographs. And
Yeah,
I'm not sure that the cost of a weight-bearing CT scanner would be a whole lot more than radiographs. Once you could convince the clinicians to rely on weight-bearing CT instead of the clinical radiographs they now rely on. So that yeah, there'd be an insurance question there. In terms of the prescription model, I think as it is, Jason can probably correct me if I'm wrong. I think that when these braces first came out of the gate, they were mostly being paid for out of pocket. But I think some progress has been made, and that's with the prescription model that's just kind of more classic prosthetic fitting instead of any kind of modeling to help in the prediction. But so I think there is a movement towards getting more insurance coverage as the value is shown more. Jason, do you have experience with whether these are covered by insurance?
Yes, and so there, as you point out, there's kind of multiple layers to this. And so one is the imaging piece and accessibility of the scanners. And the nice thing about the weight-bearing CT scanners is that they're much lower cost than a traditional CT system, and they can sit in a clinical environment, which is a benefit there. They aren't as widespread, obviously, as a traditional CT scanner. So I think that's a potential limitation. For the carbon fiber bracing, they were initially provided in a military and a VA healthcare system within the United States. And so that you get unique access to care in those settings. They are now gaining more widespread use in a traditional clinical practice. And some of that is because the manufacturers are really streamlining their processes and making the cost palatable. It's not a profit generator for most clinics, but they can at least break even when they're providing the devices. Our hope and what our data is suggesting, though, is that you don't need as complex of a device to get the offloading benefits that we're looking for. And in one of Don's figures, because of the muscle forces, the joint reaction forces are sometimes 4 to 5 times greater than body weight. And so a modest reduction in muscle forces can get you a corresponding reduction in joint reaction force. And so again, there's multiple layers, but if we can come up with a more streamlined, low cost, potentially mass producible device, then that makes it accessible to a wider population.
Yeah. Oh, thanks. And then just really quickly, do you think do people have to wear this for the rest of their lives, or are you thinking that, where's Don? Oh, there you are. Or are you thinking that you just wear it for a couple of years to get you past, keep stresses low for a while, and then you don't?
That's the next grant proposal.
Oh,
So
okay.
the first one's been in, but yeah, I think a lot of the mentality in decreasing the risk of post-traumatic OA after a joint injury has recently shifted to the early post-injury period. And so I certainly imagine that a brace like this could be used for a short period of time and provide that benefit before the joint returns to its health. But we don't really know yet one way or the other.
Andy, please go ahead.
Hi, Don. Thanks a lot. I was just wondering, you seemed like the bracing that you're presenting seemed to be consisted of 3 parts. Is that the part or the brace around the shank, if you like, the element around the foot, and the piece that kind of connects the two. And I was wondering, you presented in your results that, from no brace at all until that lower stiffness condition, you saw that reduction in contact stresses. How much of that could be attributed to, say, just the foot piece in isolation versus needing all 3 of these components?
It's a good question, because it is a rigid foot piece, so it is definitely restricting ankle motion some. But I think you don't get I don't think you get the full benefit of that reduction in the force in the gastrocnemius or soleus without that strut in the back. I do think there's potential even in some of the designs to have a load transfer path that kind of goes past the joint entirely, because since it's custom made, that kind of superior attachment to the shank can kind of do load transfer at the tibial tubercle. So we haven't modeled that yet, and we've kind of just been working on this one element of it. But honestly, when I started, I thought that that was a piece that we might explore more. We just haven't gotten to it yet.
Sure. Excellent. Thanks a lot.
Amir?
Hello, it's Amir from University of Eastern Finland, Kuopio, Finland. Thank you, Don, for the excellent presentation and very interesting. So my question is about this discrete element model.
Are you dialed in from Finland?
Yes, yes. Actually, early this week, I was talking with Rami. He was just back from the trip from Iowa, and he talked about this ankle model and this stuff. And just a day after, I received this email from the seminar series about this presentation, and it was really, really interesting.
Great, good.
I was looking forward to this presentation, actually.
Yeah.
Thank you. So my question is actually about this discrete element method model, actually about the inputs specifically. So as you explained, the inputs are flexion angle and let's say the joint contact force. So what I'm wondering is that how did you control the abduction adduction angle? Was it just a fixed angle, and if it was fixed, then how did you initiate the contacts or let's say the joint alignment in that direction?
Yeah, we kind of rely on prior work in the laboratory that shows in the ankle, it's the articulation itself that dictates the motion more than other parameters. So in general, we don't explicitly model the fibula. So in order to simulate the mortise that kind of holds things together, we have a spring in that direction that resists motion to escape. But otherwise, we allow the talus to rotate in kind of what we would call, I guess, inversion, eversion, or internal external rotation as needed to accommodate it. So it's really being driven by the tibio-talar contact stress and force transfer. That's what's driving it. So we're controlling that 1 degree of freedom, the flexion angle, but we're allowing the others to adjust as needed to accommodate the applied load.
Okay, so
in fact, some of the early stuff we did in this area with finite element, that was the key breakthrough, is when we realized you really didn't need those. And if you tried to control those based on kinematic data or whatever, it's kind of like you just locked the system up. So all you do is get really high contact stress that you couldn't solve the problem.
Yes.
So until you kind of get it to where you reduce the constraints to a reasonable amount, it doesn't work. And the DEA is just an extension of that work we've done with finite element analysis.
Mm-hmm. Okay, good. Thank you.
You're welcome.
Osman, please go ahead.
Thanks. You've been talking about stresses and this contact forces. Can you relate this to gait improvements, such as with different configurations? You show 3 different orthoses and different stiffnesses. Is it like when the person wears this, are their ankle is generating less torque or less mechanical work or more? If this changes other joints such as hips or knees, are they behaving differently based on the different configuration of the AFO? And then does the AFO do any positive or negative work? Maybe less of a positive work, but maybe more absorption, whether this changes gait or not. Also, you may not have metabolics here, I guess, but could you comment on this between different configurations? Would it improve the gait, such as less energy consumption or less variability in step frequency or step length or higher speed walking?
Yeah, you saw that one slide that had all those papers that had been published. I wasn't a co-author on even one of those, but fortunately, Jason's on the call, and I think he's explored a number of those areas you're talking about. Jason, would you care to reply to any of those questions?
Sure, I'm happy to jump in. And so the device is a relatively stiff device, and as a result, it constrains ankle motion. And so you limit both dorsiflexion motion, and you also limit push-off power. What we typically see is push-off powers in the range of 40%, 30 to 40% of normal gait. And so with that reduction in push-off power, you do see carry-on effects In some ways, when people are wearing these devices, they walk somewhat similar to somebody walking with a prosthesis. And so you do see compensations proximally. And there are, in some of our prior work, we've linked specific design modifications to altered mechanics. So if you adjust the alignment of these devices, you can have large effects on knee extensor moment, for example. And so the short answer is yes, there are carry-on effects. But for most of the people who wear these devices, especially the severely injured ones, we actually see quote unquote improvement or normalization in gait mechanics because we take them from a very painful gait pattern. We provide adequate support to keep them out of a pain-free range. And so there's an improvement or a potential normalization of gait mechanics, but also we get the symptom relief with them.
Okay, thanks.
Brent, go ahead.
I beat Reza. I just thought of, when Jason mentioned pain, I thought, I don't know if you presented any information on pain. It's something you could assess probably relatively quickly. So, what do these patients say that they feel more comfortable or they feel less pain when they do wear these devices? I guess for Don or Jason.
I'm thinking if I stay quiet long enough, Jason will hop in again.
Sure.
And then I also want to hear why there's rocks in Jason's gait lab.
Sure, I can take that as part two of the question. So for the first part, the devices were primarily developed for injured service members initially, and so they experienced catastrophic limb injury, so significant soft tissue injury, joint damage, and others. And so in those groups, we show sometimes 30 to 40% reduction in pain. And so we see associated improvements in quality of life and other factors. The really exciting thing about this work is that we're trying to prevent all of that pain. And so we have had individuals come in who do have pain. Actually, happened to be a service member. It was one of our participants, I believe, in the data that Don shared. And so that person did report some reduction in pain. But really our goal here is to reduce that contact stress and get out ahead of it so that we're preventing the arthritis rather than addressing it later on. And then the second part is the rocks are an extension of some of our work related to walking stability and falls. And so I've conducted studies in the past with modifications to amputee gait on uneven terrains, and we're looking to continue some of that work with carbon fiber bracing too.
Great, thanks.
Reza, go ahead.
Okay, thank you. Great presentation, great work. It's really hard to model finite element model the ankle and the cartilage there. I was wondering if you faced any challenges for measuring the thickness of the model, because it might have a profound effect on the final stress you measure.
Yeah, it's a good question. So, and since we're doing the discrete element analysis in this kind of most recent work, we're having to assume the cartilage thickness. We don't have that from anything. So the cartilage thickness, we had done prior work that showed that the cartilage thickness in the tibio-talar joint is pretty consistent, uniform over the range here. You're looking at 1.5 millimeters or so on each side. And the data, again, it's like published, the distribution is actually pretty uniform. So we have just relied on uniform measures. And part of the argument has been, these are people who are injured, but they're otherwise healthy. So they have kind of automobile accident, fall from a height. So there's no reason to think, for instance, they have arthritic ankles with reduced cartilage thickness. And in fact, pre-existing arthritis is one of our exclusion criteria. So we just model it as a uniform cartilage thickness, and that certainly would influence the results.
Yeah, that's exactly.
I appreciate what you said about the difficulty of the finite element analysis, because that was like a lot of really late nights for me. Actually, I inherited it. It was for a while. It was like the graduate research assistant killer. Every graduate research assistant who took on the project lasted about 6 months before they went somewhere else. And then I took it on as a staff engineer, and it was a couple of really, really late nights before we finally got something to work.
Yeah.
So now we've built on that. That was 15 years ago now, but.
Makes sense, yeah. And another question that I have is about the contact definition. Because the images you show, it's just a single cartilage, but do you have two cartilages facing against each other?
Yeah, you have two cartilage layers. So at any given point, you're just making a simple calculation about the proximity of the bones. And if they're within that cartilage thickness, combined cartilage thickness distance, then there's going to have to be a force that's produced there associated with the deformation of the cartilage, presumed deformation of the cartilage.
Oh, okay.
Yeah,
And-
it's like, it's a little, you didn't ask it, but the discrete element analysis originally was much more like finite element analysis, where you kind of had a stiffness matrix that you inverted and you did a solution. But these discrete element analysis methods have been kind of more broadly used now to just be able to resolve these kind of overclosures with local force or contact stress.
Yeah, can imagine. The last question I have is the material property and behavior of the cartilage, the mechanical behavior. Do you think we can go for elastic, or we have to make it more advanced and complicated?
Yeah, so I think it's pretty uniformly agreed now that at the rate a person walks, the rate of loading in cartilage, linear elastic is a reasonable approximation. I think when you go to more complex material property representations, it's usually because you're trying to understand failure mechanisms. So if you start to introduce something like a fibril reinforcement for collagen, for instance, or you're trying to look at kind of fluid flow, then those offer an opportunity that we used to just kind of write about abstractly, but now really you can look at failure in the collagen within that. But I think for kind of simple production, I think of this as kind of a coarse modeling approach. All we're looking at is contact stress. There's nothing in there about shear. There's nothing in there about other elements of the stress state. But it's linear elastic with material properties pulled from the literature.
Okay. Great job. Thank you.
Thanks.
Rob, go ahead.
Don, I'm sort of following up on Brent and Osman's comments and questions, and really to do with how long you think the patient is meant to wear this. Is it short term for other recovery things to take place? And I ask this because I have an ankle injury, and I get periods of acute pain, and so I use a brace that's continuously variable, but I use the brace because if I don't use the brace, the pain leads me to change my gait and I limp, and that causes back pain. So then it goes through everything else, and so I use this continuously variable brace, and it's called a walking stick. And I hate to. I'm just wondering if you're going to use a brace for a short-term period, how does it compare? What's its advantages and disadvantages with the walking stick? Because when I use the walking stick, I pick it up immediately, I have pain, and I focus very intensely on using a very correct gait so that at no stage am I causing problems into my lower back. I'm just taking the strain out of the joint. So can you model the ankle with your finite element modeling, adding a walking stick? And how do you think this brace stacks up against the walking stick if it's meant for sort of short-term use?
Yeah, I don't know if Jason will be familiar with the walking stick, but I think whether it's short term or longer term, I do think the custom fit gives you capabilities in terms of supporting load transfer potentially more comfortably. As Jason was saying, it's kind of based on the idea of a socket fit for somebody who needs a prosthesis because they've amputated the lower part of the limb. So I do think there's an opportunity for kind of customization, giving you a better load transfer. Now, we've been trying to push towards less complex brace designs with a local manufacturer, just because if it's thousands of dollars, it's not going to fly as much as if it could be a little more reasonable price. And then I think if you had a brace, why wouldn't you pull it out every once in a while if you had pain? But our objective is a short-term bout, I think, ideally, short-term bout that would provide benefit.
How important is it to get a perfect fit of the brace on your leg? Because when you tie things on your leg and you walk and they wiggle and they loosen,
Yeah.
and how critical is it to get a perfect fit, and how long can a person tolerate wearing it?
Yeah, I don't know if you could see some of those brace designs. They've even started to incorporate some of those fancy ski binder type systems with boas on them. So you can kind of have very nice cable, even load application of these. So I don't know, that's a good question. I don't know how well they need to fit. I can believe that a better fit might actually be less pain than not as good a fit, even if it had to be a little tighter.
And maybe I can jump in. I think part of it's
Do the people say that they're comfortable?
And so I think part of it is kind of what you're going after. Oh, can you hear me okay?
Yep.
And so the mechanism we're going after in the data that Don shared is really minimizing the ankle moment. And so if you do not have a device that is well fitting, you have a lot of motion before that device begins to have an effect. And so we actually have a notice of an award for a grant where we're going to look at the relative stiffness of different device interfaces. And so if you're not essentially restricting the motion, reducing the moment using the device, you're not having the desired effect. So in that case, having a well-fitting device is important. We put out a paper a year or two ago in a group of over 90 patients, and they rated the comfort as high, and they wore it for, I think, 11 plus hours a day. And so in some populations who have severe injuries, it's critically important. Whereas if you're doing something where you just need to provide a little bit of support to the ankle, as long as the strut stiffness is having its effect of reducing moment, I think the interface is probably less critical.
Yeah, well, that sounds like good feedback to wear it for that long and be comfortable. Thank you, Doc.
You're welcome.
Arash, please go ahead.
My question is about this, the goal of the project, basically. If the goal is to reduce the ankle contact force, I was wondering if you have tried to compare this using brace instead of versus gait retraining. For example, if you have smaller steps, then the contact force would also be smaller. And if the brace itself, I think you partly answered this question, but if the brace itself changes this, for example, the step lengths, and that also reduces the contact force. And if it doesn't, then as you mentioned, it is possible that basically the force is transmitted to another joint or another part of the bone.
Yeah, I haven't considered gait retraining. I don't know if that's on your list, Jason. That certainly could be another option. I guess I think of all the workout in the literature, any kind of gait retraining, it seems like invariably they run into what you're saying, where a nearby joint ends up carrying more load and it just works its way up the chain. I do think sometimes there's benefit to having the ankle close to the ground, but nonetheless, I mean, I think the shorter term brace use is potentially superior to something like a great gait retraining strategy. I just haven't thought about it much.
Yeah, I agree that in short term, probably it would be better to go with something that helps the patient or participant to deal with the pain, and later on probably another intervention might be interesting to get.
Great, thanks.
Thanks.
I have a question, Don. Do you measure the deformation of the vertical strut, I'm curious about how that deformation timing corresponds to like your ankle moment or muscle force timing.
Jason, do you have markers on the brace?
You've tried some marker tracking, but given the resolution of the motion capture system, we have data, but I wouldn't put a lot of stock in that. Just because, I mean, we're tracking with, I think our validity data is right 0.7 of a millimeter or something like that. And the deflections of the strut are still relatively small. A colleague at Imperial College of London used strain gauges to look at that also. And so there is some, again, we've had multiple discussions on his data in terms of what it means with the strut potentially bending backward during loading response and then deflecting as you might expect as the tibia progresses over the foot. At the end of the day, our kinematic data suggests that there's between 5 and 7 degrees of motion between the proximal cuff and the foot plate. And so it's not a large deflection, but it does line up with what we'd expect looking at the ankle moment curves.
So from that, are you able to see, is the maximum deformation typically happening during peak ankle moment?
Yeah, so it's providing a mechanical constraint to the tibial forward progression. And the data that Don showed with the load soles are also nicely support that. So essentially the force is being transferred from the proximal tibia into the cuff. And that's the point of force application that's reducing the ankle moment required by the individual. And so because the moment goes down, the forces on the forefoot drop by up to 50%.
And then my one other question, and apologies if you said this, Don, is the zero stiffness condition no brace at all, or a braced without a strut?
Well, in the context of the OpenSim model, it's no brace. I mean, it's essentially a standard gait model then. So there's no restriction at the ankle joint to reduce moments. So it is no brace.
Okay, got it.
Yep.
Brent, go ahead.
Whoa, we're in extra time now.
I didn't know, Don, that you did the FEA work for the rabbit studies. So these are like the Radin rabbit studies.
Yes, they are.
Okay, so one of the goals of those studies was to figure out if OA was sort of a bone up or a cartilage down kind of thing. So
it's an yeah, and it's kind of like it's reemerged, hasn't it?
Yeah. So where are you at with that whole argument?
Agnostic. At the time, we were just trying to see if impulsive loading. So I mean, now you're down in the weeds. This should be an offline conversation, but that work was trying to see, they had two different rabbit input. They had cam loading to rabbit ankles. One was more impulsive than the other, but otherwise they had the same peak forces. And the more impulsive load caused arthritis in the rabbit model, whereas the less impulsive load did not. So then there was a question about whether somehow the details of that impulsive load transfer would somehow change the cartilage stress meaningfully.
I don't remember that study being like that. I don't remember them matching on force magnitude. I remember there being a condition that had impulsive loading and then a condition that didn't have impulsive loading. But the condition that had the impulsive loading had way higher magnitudes because it had the impulsive loading. That's what I thought. I could be wrong. But I know I've gotten in a lot of bar arguments at ORS about whether or not impulsive loading is, creating the damage or not.
Only at an ORS meeting, huh?
Yeah.
But then I think bone first versus cartilage first is kind of a much bigger question that I think is very interesting and not the subject of today's talk.
Thanks.
Sure.
Other questions from the audience? Tim, please go ahead.
Don, I really enjoyed that talk. And I just have one question. And I'm looking at this from a synergistic muscle force sharing question. Did you see a proportional reduction in the forces across your different stiffnesses for your brace between the soleus and the MG muscles?
So in the OpenSim model, Jason was trying to explain this to me earlier. In the OpenSim model, the fact that you have a biarticular muscle group and a monoarticular muscle group kind of makes it so that the simulation kind of staggers a little bit on the gastroc versus the soleus in that configuration. So I think we saw gastroc behaving like we kind of expected, and then the soleus was not behaving quite the same way. And I think that's because of some complexities in the OpenSim modeling.
I see. Okay, so the OpenSim, yeah, I was just curious if you saw a proportional, because I wouldn't expect a completely proportional reduction between the two, but I was just curious.
Yeah. And the OpenSim model had a clearly differential reduction in force between those different muscles. But we just kind of, it does not agree as well as what we observed in the muscle excitation pattern. So that's kind of where we're stuck a little.
Okay, well, thank you.
Sure, my pleasure. And thank you for telling me that Monday's a holiday.
Benno, go ahead.
I have to come back to the question that Brent started. Give me a reason why you expect that impact loading should be more dangerous for osteoarthritis than active loading. Especially if you take the fact that in actual life, the active forces are about 5 times higher than the impact forces.
Yeah, I don't have an argument. I was trying to present what was Eric Radin's argument at the time, which he had kind of an argument that he'd identified a group of what he called microklutzes, people who just the way they walk, they had higher impulsive loading to accomplish the same gait as somebody else. And he was exploring the possibility that that might explain somehow the development of arthritis in those joints. But I don't really have a strong feeling about that.
I have a strong feeling, but in the opposite direction.
I got that sense. Yeah. Well, it's based on a lot of experience, clearly. So yeah, and I don't know, I think he got a lot of pushback even then when he was making that argument.
Yeah, but it still was used like a dogma. Anyway, thank you.
Oh, you're welcome. Welcome.
Any final questions?
Okay, anybody who's still on, if you want to reach out to me while I'm in town, I'm kind of open for business. Love to talk with you about any subjects whatsoever, and take plenty of input about favorite restaurants and places in the mountains to hike. There's another question from outside of Calgary.
Go ahead, Rob.
A really fast one. The issue of wearing the brace and causing instability and transfers to other joints. What if you put the same brace on both legs? You're only treating one leg, but if you put it on both legs, then at least they'd have a balanced gait. What do you think?
So I think one of the biggest challenges we face is people don't like wearing devices. And I think that goes for most devices in most cases. And so what we've heard even from some of our early participants in this particular study is that they've agreed to wear them when they're doing more demanding activities, but not when they're around the house and other things. And so I think there's this kind of self-titration of device wear. And if it provides them tangible benefit in terms of reducing pain at the time, then it's great and it's easy to sell it. When we're using it as a preventative measure, I think there'll be a proportion that will wear it But I think time will tell, but trying to get people to wear 2 devices when they could potentially only have to wear 1 might be a better solution.
Yeah. Do those same people have a walking stick for little acute moments?
Not that I'm aware of.
Okay, thanks.
Great. I don't think I see any more questions, so please join me again in thanking Don for his presentation, and thank you to all the audience members for their questions. I hope everyone has a great day, and I hope to see you all at the seminar again next week.
Thanks, everybody. Thanks for coming on, Jason. I appreciate the support.